Okay, today's lesson is called linear regression. If I were to make a bunch of data like that, do you get that I could do what's called a line of best fit and put a line through it that goes kind of like that? Now you can do that by saying, well, this point and this point work pretty well, so we're going to pick those 2 points and draw an equation that goes through those 2 points. That works. The calculator does this really complicated process where it takes all your data and it figures out exactly where that line should go, and it does not just use 2 of the points to make a line. It does it by basically averaging the differences from the line so that this line, which I thought I drew pretty well through the data, would be better than, for instance, that line, which misses all the points by a little bit more. It's like, how far is it away here? How far is this? How far is that, that? It averages those distances and gets it down as small as possible. That's called a least squares regression line. You're going to be doing that today. The calculator will do it for you if you know how to put it in. Okay, so this is really important that you stay with me step by step. And the first thing I want to do is give you a helper in case you get lost. Like, oh, what did he just say? Because, you know, you get one step behind and it's really frustrating. Rows 1 and 2 don't have to slide next to each other. Just make sure that you know they're your first call for help. Okay, rows 3 and 4, you're the person across from you, they're your first call for help. Then 5 and 6, same deal. If you need help, ask them first, because sometimes they'll know. If you get past that where neither one of you knows how to fix the calculator issue, then raise your hand and one of the 2 of us will come over. Okay, all right, so I'd like to start by looking at this data right here. You see the power plant there? This was a stat that shocked me, but then when I thought about it further, it made sense to me. In China, they are putting up power plants at a furious pace, which makes sense. If you have like 1 million people, you need the power to give 1 million people power? You can't just run your old power plant harder. I mean, they can only put out so much power. So if you have 1 billion people, which they do, they have more than 1 billion, like 1.3 billion, and their population goes up by like 2%, you just gained quite a few million people. So you need quite a few power plants. So think about that. Every year they have to add more power plants. In fact, every approximately 2 days, they're putting up a new power plant. They're opening the doors on a new power plant. Isn't that shocking? Like another power plant every 2 days. You think they're shutting old ones down? Well, every now and then you got one that's too old and has to be shut down. But that's pretty much just a net gain of like a power plant every couple days. Like since the beginning of school, they've probably put up 20 power plants. So anyways, there's a lot more power plants. And then that means, sadly, they pretty much all put out pollution. And that's not a good thing in anybody's book, whether there's, whether you're going to talk about climate change being, geez, we still don't know exactly how much of an effect, blah, blah, blah. Nobody would say more pollution is good. One of the things that's one of our best hopes, and I know I'm spending a minute on this, but I think it's really cool, and I hope it happens in your near lifetime, as in fairly soon. They're really close to harnessing nuclear power, which I know there's already nuclear power plants, but there's 2 kinds of ways to do nuclear power. The kind we do right now is the easier kind. We mastered that many years ago, and that kind creates nuclear waste. Have you heard about the other kind of nuclear power? There's fission versus fusion. Yep. And fission, it's fission or fusion that we do, that's the new one that they haven't mastered yet. Fission? All right. Fusion is one where they put them together, and fission is where they split them apart. So what I'm asking is, I don't know which they currently do and which one's new. You think they split them right now? Okay. All right. So there's fission and there's fusion. Okay, and the one we're doing right now is basically creating a whole bunch of nuclear waste. The stuff will be nasty for like thousands of years. As in, like, if you heaven forbid, touched it, drank it, you'd get really, really sick. Okay, so the new kind of power plants will give you about 10 times as much power, and they have no bad waste. There's no terrible waste. The only things that come out are hot air, like the top of the smokestack. This could just be steam coming out, and one other thing, carbon dioxide, which is what plants give off, and we breathe out, and it's not terribly poisonous. So the point is, there's a day coming, and I hope it happens in your lifetime and soon, where we'll have way cheaper power and it won't give off nasty side effects. So it's coming. And when you combine that with another thing that they're really close to getting, which is called superconductivity. Have you heard of that before? That's going to allow trains to, for example, levitate off of train tracks. And can you imagine how much easier it is to push a train around the country if it's levitating? And superconductivity seriously can do that. And you add that in with really cheap power, and holy cow, we can be out of this whole pollution thing really quick. Just got to get those two advances. And back to the power thing. This is what's happening right now, though. We're using more and more and more and more and more and more power. And it stopped in 2000. It's currently 2018. It's going to be 19 soon. And do you think it stopped? No. If anything, we really ought to look at the data and see if, I'm not going to do this right this second, but actually I am. It's right here. If I graph it, is it making a straight line or is it actually going exponential? If we were using way more and more and more power, it'd actually be curving like this. There's something called an exponential regression too. We don't have to worry about that today. We're just doing linear ones. But do you get not all data goes in a straight line? That makes sense? So today we're doing linear data. Next test, it's the same process, except you're not going to choose linear regression. You're going to choose exponential regression. And it'll be exponential data. Like, what's something that's going up exponentially? Yes. Population. I would agree. Population is not just a straight line growth. That's good enough. All right, so there are things that go up exponentially. There's things that go up in a linear fashion. And there's even a third kind we'll learn later. So today it's just all about linear regression. If you put this stuff in your calculator, you can get your calculator to tell you a straight line that would go through all the data. That's our goal. So I asked you a while ago to hit the stat button. And once you're there, if there's any data on your calculator, you're going to see it as soon as we hit edit. Hit enter on the edit thing. And I've already got data in my L1 and L2 lists. Now, you can by accident wipe out your whole list so it's gone. And then I have to do a really complicated thing to your calculator to get it back. Okay, so please don't try to delete the whole list at once. Just hit DEL. Yes, there's a way to do it. I don't want to try to train you because you do it slightly wrong. You're going to wipe your whole list out. So just hit DEL to delete each little thing in your list. If you had nothing on your list, yay, you saved a few keystrokes there. Okay, now in L1 and L2, which do you think is like X? L1. That's the one to be on the left-hand side, right? So let's put in the year, which is time. Thinking about it for a second, is there a spot where time is supposed to go if you're picking? Yes, there is. X or Y. Time goes down here. It's called the independent variable. Time goes on the bottom. Yes, time is your X, so it's your L1. So in the L1, we're going to put the time. We're going to start with 1950, so everybody type 1950, enter. And then type in 1960. And then just keep doing that until we hit the year 2000. I'm going to pause for a second while I type in the data. Now, I would strongly recommend looking back. Do you get if you typed one key wrong in that whole process? And by the time we're done, we're going to have typed 60 keystrokes. You do one mistake and not notice it, your data is off, your equation will be off, your answer will be marked wrong. Do you get what I'm saying? If I just said, what do you think is the probability that a kid is going to type in 60 things exactly perfectly? There's not a high probability that everybody does that right. So check your list, make sure you did it right, and then go over and do the energy usage in your L2. So 34.6 here, etc. I'm going to pause for a second while I answer. Okay, got all your data in? Now this is kind of like a Google Doc. You do not have to save it. If we go somewhere else, it'll still be here. Don't worry. It doesn't go away unless you specifically go to each little cell and hit delete. Okay? So this will stay here forever unless you go and personally hit delete. So I can get out of this by hitting the stat button again. And now where we were was called edit. Where do you think we're going to go next? Calculate. Calculate over here. And in the calculate, I have a few choices. I'm going to show you how to do what's called one variable stats. Why? Not because of today. This is a little side thing I'm going to do to help you with the ACT. Okay? The ACT has stats on the list of things you got to be able to do. Okay? There's quite a few little stats you'd have to know. Mean, median, mode, range. The mode is the one thing that the calculator is unable to do in one variable stats, but it does more things too. Do you remember, by chance, box plots? They're kind of a big deal in stats. If you ever take a stats class, they will for sure be doing box plots as one of the earliest things, and it involves Q1 and Q3. Does anybody remember where they would go? By the way, this is also something that could be on the PSAT test. Is expecting you to know basic stats. Remember? All right, I think I understand what you mean, and I'll show you for sure. This is your minimum, your smallest number that you have in your data set. If we use the years that we just typed in, do you remember what the first year was? 1950. Okay, so then that's the minimum that goes here. What was the maximum, the highest number that we had? 2000. Do you get that somewhere in here, actually I'll move that a little bit, somewhere in here is actually the very middle of all of our data. What's that called? The median. Okay? The median of our data would be somewhere in here, kind of in the middle. And the calculator can tell us that number. It'll be on our one variable stats list. Also, this is Q1 and this is Q3. Do you have any clue what Q stands for? Quartile, yep, quartile. So this is the first quarter in here, as in 25% of our data will be between 1950 and Q1. That's where 25% of the data is. Okay, so it divides it up into 4 quarters. All right, this is the second quartile. Notice there's no Q2. Q2 is kind of like the median. Then Q3 is from here to here, the median to Q3, which I don't know yet. I can look on our one variable stats in a minute. But in case you wonder what the heck are Q1 and Q3, they're things from a box plot that divide your data into 25% chunks. 25% of your data is from here to here, 25% is from here to here, and the other two 25% are in here, and they total up to 50% of your data is in the middle. Okay, so there's a little teeny tiny stats lesson. Go back in here and do one variable stats. Hit enter. Now, your calculator will either do what mine did. Raise your hand if yours is like that. Congratulations, you have the newer calculators. If yours didn't do that, you have the older calculator, and you have to tell it what list you want to do the data on. But the cool thing is, it will default to list 1. Do you get most people put their data into list 1? Your calculator is smart enough to know that, so if you just hit enter, it'll go to the right list. Same with us on this way. We just hit enter. Freak list, you don't have to do anything. That's the frequency of the list. Hit enter, enter until it's done and it actually does it. Do that, please. Everybody at this point, no matter which system you have, you just hit enter there. And yay, I've got my one variable stats up. What do you think X bar is? It could be the median, it could be the mode, but it's not either one. The mean, as in the average. Okay? The average is 1975. I need you with me up here. You're going to fall asleep if you do that. All right. This is the X with the little squiggly thing next to it. That's called the summation. That's all the years added together. You see how that would be handy sometimes? It just added every number on the list for us. Then don't worry about the sum squared. That's something that you do when you're doing linear regressions, for example. If you had to do it by hand, that's how you could do it. And let's move down to this. The one at the top of the list now. I guess I can't move it up any higher. That one's called, anybody know? I'm just curious. You know? Did you take a stats class or something? Ah, there we go. So this must seem like baby stats to you, because this is the stuff you probably learned in like day 2. All right. So this is the standard deviation. All right. So standard deviation, the way I would describe it is it's the average of how much things deviate from the average. Like I would say the amount of money people have in their pocket right now. Do you get if I said the average amount of money that somebody has in their pocket right now is $1.78? If I said that, could you believe that's possible? In your pocket right now, the average was $1.78. Okay? Could there be one kid with 40 and a lot of kids with 0 and then one kid with like a buck? Yeah. So how do you say how much is it varying? Well, if every person had $1.78, standard deviation would be 0. As in nobody deviates from the average. You all have $1.78. Okay? But if it's big deviations, like one person had 40, one person had 5, and nobody else had any, then the standard deviation was big. And the standard deviation might have been $2. Anyway. So, standard deviation is not something we need you to know. I just wanted you to briefly get a little stats out of this. Here's Q1, 1960, so I could put that here. 1960 goes there. All right, so enough on the stats lesson. Other than you got median here, that's handy. You got the max and Q3. Okay, so that one button that I showed you can answer like 8 different ACT questions that could come up. See why it was worth a second to show you that? It's called one variable stats. All right, now, could you have done some of them in your head? Sure, you could have. But Q1 and Q3, those are kind of tricky to do in your head. And they are on the list of things that are approved for the ACT, so you could get asked that. All right, moving back to stats again, because now we're going to do the thing we're doing for real, which is over on Calculate. Does anybody see it? 1, 2, 3, 4, 5, 6, 7, 8. Which one is it? It's number 4. So I'm going to hit the 4. It's called Lin Reg. Now, once again, we have the division of some people have the screen I have. The newer calculators look like this. The older calculators do not do that. They just say the word Lin Reg. If yours says Lin Reg right now, I got a spelling issue, hold on, which stands for linear regression, again. If yours just says Lin Reg, you're going to have to type something. If yours look like mine, you're still going to have to type something, but some of it's already filled in for you. Just take a guess. What are these people that have the calculator that says Lin Reg going to have to type that was already pre-filled for us? L1 and L2. So if you have this older system, you have to type L1, comma, L2, comma, Y1. Now, I know you don't know where Y1 is, but somebody smart in here probably knows where L1 and L2 are. Do you see them? Where is it? Above the 1 and above the 2. Very good. So if you need to type in an L1 or an L2, here they are, right above the 1 and right above the 2. And I'm going to pause for a second.
All right. So we have our L1, we have our L2, right? Everyone have those at least? All right. We are going to figure out together how to find Y1. All right? And since y1 is in a place you probably wouldn't look until it was like the last button in your calculator, I'll just tell you it's this vars button right here. So if you hit vars, you're going to get a screen that says vars, y vars, or color. If we're looking for y1, is it going to be, which of these three categories is it going to be in? Y vars, because we want that. All right, so I'm just going to arrow over. I'm in y vars, and this first one here is a function. If we're looking for some kind of equation, do we want a function? Yes. So we're just going to press 1 or enter for that one. And the first one right there is just y1, right? So we're just going to hit enter there, and you'll get y1. And so I pressed y1. It was accidentally on this X list when I did so. You want to make sure for people who have this new version that your y1 is going under the store Reg Equation. All right? So, oh, I can erase them. There we go. All right. So, erasing those, I'll get my L1 back here on the X list. I'll arrow down to this store Reg Equation, and I'm going to do that again. So if you did not get it the first time, we hit vars. We arrowed over to y vars. We hit function, and we just hit y1. So now under our store Reg Equation, we have y1. Now, this store Reg Equation, all that means is whatever equation we get from our regression line, we want to store it as the variable y1. Why would that be a good idea, to store this variable? Or rather, to store this equation? Do we want to know what that equation is? Yeah. And so if we had just pressed calculate without storing this, we would have gotten the equation once, but then after that one time it would have disappeared and we wouldn't have it again. But if we want to keep on using this equation to calculate other things, we want to store this equation so we can get it back in the future. All right? So once you have your L1, your L2, and your Y1, it should look like this on the new calculator. On the old calculator, it should just be L1, comma, L2, comma, Y1. So for those, if you have one of those two, just hit enter on the bottom here so that it'll calculate it for you. And you're going to end up with a screen that looks kind of like this. Right? On this screen, that top equation, what does that top equation say? Y equals ax plus b. So this isn't something that you know or something that you've heard, but what's very similar to y equals ax plus b that you do know? Mx plus b, right? Some of you might be wondering, why would they ever use an a instead of an m? Just as a wild guess, who thinks they know what state Texas Instrument Calculators was made in? Texas, that's probably a pretty good guess. In Texas, maybe they use A instead of M, right? So, or it could just be simple so that they can say, oh, we have A as our first variable, B as our second variable, and so on. So they're on the calculator here, they're just going to use y equals ax plus b. We know that it's y equals mx plus b, right? So if we have an a value and we have a b value here in our y equals ax plus b equation, we've just found our linear equation, right? So if we went on and said, looked at this page here, on this page it says, okay, we want this y equals something x plus something, right? What were those numbers that we can fill in? What was this a that they gave us? 1.29, okay. 1.29, and then what was this other blank here? Can someone say it? Just, can I just have one person and saying it like super loud so I can hear it?
Could you say it, please?
Okay, I'm just going to round that to 9 there. All right, so this is a 2,473.9. All right, we've got our numbers. We've got this equation. Woo! What does this even mean, though? I mean, this is just an equation, right? We know that this equation here is the equation that, like, just some kind of linear equation, right? But what does it actually stand for? And so if we look back at what the problem was actually asking about, what kind of data were we using? So, for example, our x variable. Was our x variable measuring the number of pizzas? What was it measuring? Years. All right, and then our y variable was what? Energy usage, and then it says here in quads. Quads is like the unit for energy usage that they're using here. I don't know what a quad is personally myself. I think we looked it up and it had something to do with like British thermal units or something, so we don't really need to know what a quad is, just know that that's the units that they're using for energy usage here. All right, so if we go back here, we have this y equals and then this 1.29, and we said that that was equal to a, or in our case m, right? What does m stand for? Slope. So 1.29 is our slope, but what does that actually mean for us? So if we said, okay, we have 1.29, 1.29, if it's a slope, that means it's kind of like a rate, right? What kind of rate does this represent, though? So I heard a per year, so we know that this is going to be something is changing per year. Energies in quads, right? So this is just kind of like saying, oh, we have 1.29 quads per year in terms of how many quads we are increasing each year, right? And then for this number over here, this negative 2,500-ish number, what does that mean for us? So is it years? Do you think we can have negative 2,500 years? I don't know, it seems kind of weird to me, right? What is it if it's not years? It has to be quads, right? And so this is basically saying, if, theoretically, we were at year 0, we would be making negative about 2,500 quads. All right? So we want to make sure that when we're getting these numbers and we're making this equation, we don't just end with, okay, we've got these numbers. Great, we have an equation. We want to say, what do these numbers actually represent? And so just kind of as like a measure, how many people here are planning on taking any kind of physics class here before they graduate? Or are currently taking a physics class or some kind of physics? In those physics classes, this kind of thing, we're saying, what does this number mean? What does this number mean? It's super important. And a lot of people who are currently in physics aren't getting this. You guys are like already ahead of them because you guys can get, oh, this is a rate, this means quads per year. This means something in quads. All right? So good on you guys. All right. So moving on from that, we want to do, I really don't, let's see. Okay, let's do this one first before we do our fun activity. All right. So we found our equation. We figured out what each of the parts of our equation mean. But now we want to apply our equation to something else, right? If we want to apply our equation, for example, for this one up here, it says we want to predict the annual energy consumption in the year 2013. Was the year 2013 one of our data points? No, it wasn't, right? So instead of having just a data point to look at, we want to use that linear equation that we found, and we want to predict what would happen in the year 2013. All right? So our equation, it was y equals 1.29 x minus, I'm just going to round it to 2,500 up here, but you know that it's actually like this negative 2,473.9, yes? All right. If we were to take this equation here, and we want to find the energy consumption in the year 2013, we need to take that 2013 and put it somewhere, right? Which variable are we going to substitute 2013 for? X? All right, so if we have this, we'll have our 1.29, and then we'll put the 2013 in here. And then you'll have your, here, I'll just write the number out. Great. Can anybody do that really quickly and see what they get? Once you have figured it out, compare answers with the person next to you. Do you have the same answer as them?
Oh, yeah,
Yes. All right. What did somebody get? How much energy are we using? Yes. 0.87, so I'm going to round that to 9 again. So 122.9, and you used units, right? Units, quads. All right. For this second one here, it says we want to predict when we will reach 120 quads. If we want to know when we're reaching 120 quads, where should we put the 120 quads? Why? Is everyone okay if we do not go through that problem step by step, or due to rearranging, should we go through it? We're good? All right. So for that example, we had that example. I want to do something that's kind of more real world though, because, show of hands, who here actually cares about energy consumption right now? Like, some people do. I personally am just more concerned about charging my iPad, right? So some people don't really care about like energy consumption right now. But something that might interest you is, what if I created a different set of data points where this L1 here was my height, or somebody's height, and this over here was the length of your pinky. I think I spelled pinky wrong. It's okay, right? You don't have to be good spellers here. So, if we have height and pinky length, I don't know about you guys, I don't know what my pinky length is. That's why Mr. Server is walking around with a meter stick for people who want to measure their pinky length. So, can I get about 7 volunteers?
Just one.
One at a time. But let's start.
Tell her your height in feet. I know none of us members is like, oh, I'm 63 inches. But tell us your height. Like you said. So.
All right. So, when I call on you, tell me your height as you know what your height is. All right? So, some feet, some inches, right? And then, after that, we will measure your pinky length in inches. All right? You're 5'7"? Okay.
Just a second.
I'm going to pause for just a second. So, we have 5 feet, 7 inches. How many feet are, or how many inches are in a foot? 12. So 5 times 12, 60. So this will be 67 inches, right? So I'm just going to write, I want all this in inches, so I'm just going to write inches to remind myself up here. All right, what was your pinky length?
2.6.
2.6 inches. All right, next person, yes. 68 inches, converted it already. All right, so 68 inches. While we are waiting for her pinky measurement, somebody else. Yes.
67.
You're also 67. That is okay. Do you think that your pinky length is going to be the same? Maybe. We don't know, right? 2.75 for your pinky length. And then right here, we're measuring pinky length. And then I saw another hand.
2.5.
2.5. So it was slightly different. All right. Yes. 70 inches.
2.9.
2.9. All right. Let's get someone. We've got some pretty tall people. Why not some shorter people? All right. Yes.
That was right. That was 5'6".
You're 5'6". So 5'6". 5 times 12, 60, 66. All right.
About 2.7.
2.7. All right. Let's get one more person. Who is below 66 inches? Or who's below 5'6"?
Alright.
Come on, represent. Right?
What's all?
5'3". So 63. Yes.
Pretty much 2.4.
2.4. All right.
Okay, that's
Woo. Okay. And just a fun fact: in my family, I am the shortest, which sounds like okay, whatever. Except I have a brother who's 10 years younger than me, and he's taller than me. So, it's okay to be short, right? All right. So, this is what we have for our data. On your own now, type in. This is our height. Height is going to be our x variable, so it should go in L1 or L2. First list or second list? First one. All right, and then we have our pinky lengths. And I'm going to pause while everyone gets that entered into their calculators. All right, so just for people who are finishing up, because some people are fast typers, our follow-up question for this data that we have here, that I will try not to stand in front of, is, say you found a pinky. I don't know about you guys, I've been watching the crime shows or whatever. They find pinkies a lot. So, if you found a pinky, and say that pinky was, should we go small or long? Short or long? What do you think? Long? Say that this was a really long pinky and it was 3.5 inches.
correct.
If you had a pinky that was 3.5 inches, that'd be, okay. Anyways.
This is what the test is like, too. We don't just say, put the data in, give us the equation. We say something like this, where we found this data point,
All right.
What?
So, if we found a pinky that was 3.5 inches, I want you to predict how tall was that person? Right? So while you guys are working, I'm going to pause. So, for people who have figured out this follow-up question, how tall was this person? 6'7". 6'7", so 6 times 12 is 72, right? 6'7", 79, is that what you said? All right. 79 inches. Let's see, someone who's 6'7". I don't know.
Probably a professional basketball player.
I don't know, I wonder if they have a pinky that's 3.5 inches. All right. So, because we have less than 12 minutes left, I want to quickly give you your homework. It's not a lot of homework for today. All right. For this first one, we are going to do this first one. All right. There's one thing that's different about this. It is no longer in a vertical XY table. Please don't freak out about it. Is this top row here X or Y? This is X. All right, that means that this is Y. All right, that's the only difference. All right, from here.
Which one's L?
All right. So, if we have X, we have Y. That means L1, L2, right? Okay. So, what we want to do with this, A, B, and C. All right. Find your line. Predict information from your line, from the equation that you get. Next page, here's another one. This one is the energy production one that we had done. So if you still have that data of L1 and L2, I think we deleted it when we did the pinky one, right? That's okay. So if you have the L1 and the L2, you'll just have to re-type those in, but it's along the same lines. So you have those two, and I believe that is it. Just two problems, all right?
But I strongly recommend doing them because this should be your happy place in the test. It's not a super easy test, but this is a super easy question. So, you gotta
So-
do this part.
Two questions. Because it's two questions, that means it's even easier to finish your homework, right? So definitely do it. And that will be all for today.